Welcome to the third week of 2FA3, Discrete Mathematics with Applications 2 at McMaster University. My name is Mehrnoush Askapur, and in this video I'm going to walk you through an introduction to logic and in particular predicate logic. We will start by a general idea of formal languages, and after that we will see different levels of expressiveness of logic languages. So what is logic and why do we need it? We all know different forms of communication that we use on a daily basis, including natural languages such as English, French, Chinese, or hand and face gestures, or other formats of communication. But they're not always the best means to convey certain types of concepts. Scientists and engineers usually collect data about a certain phenomenon by experiments or different types of studies. But raw data is not enough for them. They need to reach some conclusions from it. So they need a well-structured framework to reason and make arguments about the data they already collected. There are legitimate conclusions from it and communicate those conclusions with other scientists. So they need to have a language that allows them to describe a phenomenon in an unambiguous way, and also a reasoning framework that prohibits them from drawing illegitimate conclusions. And this is basically why they need to use an artificial language or a made-up language with mathematical notations or programming languages. But why do we need artificial languages? Why not using a slightly elaborated version of natural languages? The problem with natural languages is that they do not have formally defined syntax and semantics. They do have standard grammar constraints and vocabularies, but they allow for interpretations from sentences in different contexts or expressed with different tones that are ambiguous or subjective. That is why we switch to defining other types of languages, some of which you already know about, programming languages. Programming languages have formalized and precisely defined syntax, but again, semantics are usually defined with natural languages that are, as we said before, informal. So that is why we call them semi-formal languages, meaning their definitions only partially describable with mathematical notations. Formal languages, on the other hand, use mathematical notations to define unambiguous syntax and precise semantics, so that the fact that a sentence is well structured based on the syntax of its language, or if it's true or false based on the semantics of its language, is not subjective. Formal languages are a very useful tool to build models of different practical systems in order to replicate the real behavior of those systems. Imagine that we want to build a super fancy and expensive system, so we want to make sure we are not building it in a faulty or problematic way. So what we can do is to first build a model of it, analyze the model to detect problems that might occur in real scenarios, and only after that we build the real system according to the observations we made through the model. There are many aspects to a system, including its structure, like its building blocks, its components, its behavior, and also requirements. Formal modeling languages usually tackle one of these concerns through two main prospects. One is operational view, and the other one is descriptive. Operational languages describe a system with transition systems. So they have a set of states, which basically each of them is like a configuration of the system, and transitions defined between all these states. For instance, the state machines or finite state automata that we will see in the following lectures are examples of such languages. Descriptive languages, on the other hand, describe system requirements. An example of this type of languages is logic that we will see today. So with logic, we can model a system, a real system, via formally, or logic formally, basically. And so now that we have an idea that why we need logic and why is it good for, we can proceed to formally define what it actually is. Specifically, logic is an artificial or made-up language that is designed to describe and analyze phenomena or a certain aspect of phenomena. For example, like its temporal characteristics. and to make reasoning on a certain phenomenon or issue easier and more straightforward. So any language has an alphabet, syntax, and semantics, and so does a logic language. Moreover, it also has like a notion of logical consequence. Formally speaking, logic is a family of formal languages which are defined with a signature, common syntax and semantics, and a notion of logical consequence. A signature is a set of all symbols that are part of the alphabet of a language. We could inductively define terms from those symbols, and then terms could inductively create more complicated terms, and all the base symbols for that and all the constraints that those terms need to follow are defined in a signature. So it contains variables that are permitted in some languages and in some not, logical constants that have the same meaning everywhere basically, and non-logical constants and the meaning associated to them. We will see examples of signatures later when we talk about non-logic languages. And syntax and semantics probably are basically already known to you. Syntax is the grammar of a language based on which sentences could be made from the alphabet. It defines which sentences from all possible combinations of alphabet are acceptable. And semantics says if the sentences made following the rules in syntax actually make sense. Essentially, semantics associates a meaning to every syntactically correct sentence of a language and maps symbols to interpretations. Now take a moment to think about the following question. Which sentence is in English is syntactically incorrect, just to make sure you have a perfect understanding of the difference between syntax and semantics. Okay, so as many of you have probably guessed, the sentences are all grammatically sound except for A that use the wrong verb, so the answer is A. Well, we talked about signature, syntax, and semantics, and now we talk about logical consequence, which is another element of a logic language. An argument is a sequence of propositions including an arbitrary number of premises and a conclusion. All the premises being true guarantees that the conclusion is also true. In other words, an inference from one or more premise is either logically justified, meaning it's valid, or it's not valid or not justified. A valid inference could not be falsified if the premises are true. For example, we have here A is older than B, B is older than C, so A is older than C. The first two sentences are two premises, and the third one, A is older than C, is actually like a conclusion. And this is an example of a valid inference. Whatever number we replace A, B, and C with, in a way that the first two sentences are true, A is older than C, which is the conclusion, will be true, and we cannot falsify it. On the other hand, an invalid consequence is when you can falsify an argument without contradicting the truth of premises. For example, A is older than B, A is older than C, so B is older than C is not valid because you can just find three values for A, B, and C that simply contradict this conclusion. So if we think that A is 15 years old, B is 6 years old, and C is 12 years old, then the first two sentences are true because 15 is greater than 6 and 12. But the conclusion is falsified because B is smaller than or younger than 12 or C. Okay, so now let's look at the following questions and see if you can correctly answer it. Is the following a valid consequence? Person or student A attended engineering school or med school. A attended med school, so these two are premises, and the conclusion is so A did not attend engineering school. You can pause the video to think about this for a second. Okay, so let's see if we can find out if this consequence is valid or not. So let's show A attending engineering school by E and A attending med school by M. So the first premise says A attending E or M. So E or M. And then P2 is A attended medical school. So M. And then the conclusion is A did not attend engineering school, so not E. So we want to see if both premises are true. Is it possible to falsify the value of C or not? So, so let's see what happens if P1 and P2 are both true. So basically, if P2 holds, meaning M is true, then automatically P1, regardless of E being true or false, is true because we have M here, right? So we have two cases in which P1 and P2 are both true. One in which E is true and one in which E is false. So in case E is true, negation of E is false, right? So we have a combination. So basically we want to prove if hypothetically this implication could hold or not. And what this combination is showing us is that there is some setting in which we have true on the left hand side and then we have false on the right hand side, which is, well, something which is false, and we don't want this, and that says that this conclusion could be easily falsified based on the two premises, and thus it's not a valid consequence. But let's see what would happen if we had a different premise. So let's say that the first premise is still E or M. The second premise is A did not attend med school. Would that say something certain about the other part? The other part being, okay, so if not med school, then A attended engineering school. So let's see what this one gives us. So again, we want to see what happens if both P1 and P2 are true. If P2 is true, then it means M is false, right? So if M is false, then the only way for P1 to be true is that E holds, or E is true. And that basically is what we have here. So there is no cases in which we have true here. This is a question mark, and false here. So we cannot falsify this based on these two premises. So if we had not medical school and so the A did attend engineering school, then that could be a valid consequence.